10 years.
10-year increment, yeah, 10-year DBH increment. I also, from stands, it says here from stands a similar composition. Okay, fine, whatever. Inferred that I would have these mortality rates for 2, 4, 6, 8, and 10-inch trees. Presumably no mortality for trees larger than that. So there's my mortality component, right? Survivor growth component, mortality component, and then I'm just going to assume that over a 10-year period I might expect 60 trees per acre growing into the 2-inch class. That's my stand-in growth. How many new trees? What regeneration is going to rise up into the 2-inch DBH class? And the example you'll see here, I use 2-inch classes, right? So the smallest class is, well, as long as I'm not considering trees less than 1 inch, is 2-inch trees. And then finally, I have an example of a local volume equation that gives me tree volume as a function of DBH and DBH only. And since I'm not differentiating between species, I will use that equation for all species of tree. So there are my inputs, right? That's my starting point. That's the information I need to conduct this stand table projection. So now let's conduct it. It's convenient to lay out those data in a tabular form like this. Looks like something you might want to put into a spreadsheet. So I have my DBH classes listed. I only had trees, at least initially, up to, I had them up to the 18-inch class. So I have 2, 4, 6, 8, 10, up to 18 inches. I have a computation of 10-year increment using this equation. Just plug in the midpoint diameters into that equation to get increment. So there are my 10-year increment values. The next thing I did was calculate mortality. You got to do that first, right? Because I'm only going to project surviving trees. So I first need to subtract out mortality. So my assumption was that 61% of 2-inch trees will die. So 61% of 71.9 trees initially. 43.9 trees per acre are expected to die over that 10-year period, leaving me with 28 surviving trees per acre. And so forth for all the trees down to the 10-inch class, which was the last class I assume mortality would occur in. So I get this column of surviving trees per acre. Those are the trees that I'm going to grow into the future, right? Those are the only ones that are going to survive into the future. These last set of columns then are the actual projection. So in each case, what I first do is calculate the movement ratio. Remember, movement ratio is increment divided by class width. Class width is 2 inches, right? It doesn't change. It's 2 inches in each case. So the movement ratio for the 2-inch class is what?
1.04 divided by 2.
1.04 divided by 2. One, is that what you said? One, yeah, I didn't hear the 1. 1.04 divided by 2, right? Which is 0.52, right? So to interpret that properly, 52% of those trees will grow 1 class. The remaining trees, 48% of the trees, will stay put. So you see over here, I have 1 class movement, 52%. 52% of 43.9, 28, sorry, 52% of 28, 14.6 trees per acre. The remaining trees, 28 minus 14.6, stay put. Wait a minute, it says 73.4. That's not 48% of 28.
In-growth?
Yeah, it's the in-growth trees. It's in addition to that percent of trees that stayed put, that assumption of 60 trees per acre of stand in-growth. So I do that for all the diameter classes. 6-inch class, let's do the 10-inch class, the math is easier. 1.82 divided by 2, 91% of the trees move one class. 91% of 12.1, 11.0. The remaining 1.1 trees stay put. Example of a movement ratio larger than 1, 16-inch class. 2.06 divided by 2, 1.03. 3% of the trees move 2 classes. 3% of the trees, a tenth of a tree, move 1 class. Remaining, move 2 classes. Remaining, move 1 class. Okay, everybody see how to get those last columns? Why am I going to the trouble of going down to a tenth of a tree? There's no such thing as a tenth of a tree. Why don't I just round all these?
Your future projections?
Well, it would, yes, that's true. But remember, this is per acre. What if I have 100 acres of this? Should I carry some decimals? Yes. Okay, once we have that laid out, I've repeated it right here. We can start combining things to come up with a future stand table. So all those results are presented here. I start with a 2-inch class, 4, 6, 8, and now I've added 2 diameter classes. Right? We only had trees in the 18-inch class, but 10 years from now, we're going to have trees up to the 22-inch class. So I've added 2 lines to the stand table. Volume per tree, that comes from that local volume equation, right? Present number of trees, well, that's just from the stand table that I observed by cruising the stand, right? And so I can take present number of trees times volume per tree and get present volume per acre. Why don't I put any volumes down for 2 or 4-inch trees, do you suppose? Yeah, they're not merchantable. I don't care about them. From a merchantability perspective. Future number of trees. Well, the 2-inch one's pretty easy. 73.4. That just comes from there. Right? How about this 26.6 4-inch trees 10 years from now? Where'd that come from?
The percent of 4-inch trees in 0 classes plus the percent of 2-inch trees in 1 class.
Exactly. Add the diagonals. 2-inch trees that grew to the 4-inch class and 4-inch trees that stayed put. And so forth all the way down to the line, down to the end here, or near the end. For example, the 20-inch class, which it says here 1.6 trees per acre. Well, we had 18-inch trees that grew 1 class into the 20-inch class. And we had 16-inch trees that grew 2 classes into the 20-inch class. So 1.6 trees per acre. Future volume, future number of trees times volume per tree. So now we have a future stand and future stock table for our particular stand. Is that clear? Once we have that information, we can compute the components of growth in various growth definitions. So in-growth volume, 23.4 times 2.6. Where'd that come from? What tree is the threshold for in-growth volume, not stand in-growth?
Two?
In-growth volume. No, not stand in-growth, just plain in-growth. Which class?
Oh, it's the one above 4.
6 inch class. So we have predicted that we have 23.4 trees per acre growing from the 4 inch class into the 6 inch class. Right? We had no 2 inch trees that grew 2 classes. So the only in-growth there is from the 4 to the 6 inch, 23.4 times the volume per tree of a 6 inch tree. Gives us in-growth volume. Mortality volume, well, that just comes from this mortality trees. But of course, the only trees we care about are those 6 inches and larger. So mortality volume is mortality 2.1 6 inch trees died times the volume of a 6 inch tree. 4/10 of an 8 inch tree died times 5.4 the volume of an 8 inch tree, and so forth. So in-growth, what we called I. Mortality, what we called M. We'll assume there is no outgrowth. We could add outgrowth to this, right? We could say we remove so much volume, so much volume and somewhere in between. We could also calculate going through step by step what survivor growth is. But it's easier to take a shortcut. Recall that we said that the difference in volumes or basal areas or whatever attribute we're interested in is a specific combination of growth components. In particular, it's survivor growth plus in-growth minus outgrowth minus mortality. Well, we know the difference in volumes would be 1029.1 minus 652.3, right? We already calculated that. So that difference needs to be equal to this. So the difference is 376.8. That would be equal to a survivor growth, is the only thing we don't know, would be that minus in-growth and plus mortality, right? Just doing the algebra. So we get a survivor growth of 324.6 cubic feet per acre. And now we can calculate any of those definitions of growth. So net growth, survivor growth minus mortality, 324.6 minus 8.6. Gross growth, survivor growth plus outgrowth. Well, there's no outgrowth, so it's just survivor growth. And then production, survivor growth plus ingrowth. In this case, 324.6 plus 60.8 production. Okay? Any questions?
Where did the 60.8 come from?
The 60.8 ingrowth volume, right?
Oh.
We had 23.4 4-inch trees that grew into the 6-inch class. Guess I should have been moving and using these circles. Sorry about that. Yeah.
Why is the 6-inch class the?
Just arbitrary. It's what I decided that's what we're going to be interested in. Depends on the situation, right? What trees are we interested in calling merchantable? Whatever that is. Could be 8-inch, could be 4-inch.
That is what determines your ingrowth.
Yeah, that determines ingrowth, not stand ingrowth, but ingrowth. Ingrowth is trees coming into a merchantable size. Other questions? Okay, just a couple of comments on what sort of stands we prefer to apply this in. Well, obviously, just like any technique, it's only as good as the information we have. We ought to be able to do a pretty good job getting a stand table, right? We know how to get a good stand table estimate, at least one that's good enough for our purposes. The growth information, well, there are a couple big problems with growth information. One is increment cores are sometimes hard to read, right? They're just hard to read. So if you're having trouble reading those increment cores, your growth information is going to be affected. The other thing is we're assuming that future growth or really should say, put it this way, that past growth is indicative of future growth, right? And we know that's never the case, right? The dam is changing over time, and therefore growth rates are going to change. But for short periods of time, it's at least a first approximation. The two weak components, nothing we can really do about them. Stand-in growth and mortality, just going to be difficult. So we want to use short-term projections because of this growth issue. So we want to apply this, I say, in small, or is it going to be best applied, in small, understocked, multi-age stands. So why do you suppose I say small? Which is not always true, but generally if we think about small stands, wouldn't we expect that they're going to be more homogeneous with respect to growth rates? Not always the case, right? Small things can be highly variable as well, but less likely to be so. So small stands, small in size stands. Understocked. Why would I prefer to use this technique in understocked stands?
You're not gonna see a lot of ingrowth if there's too much competition.
Well, no, I say understocked. You're talking about overstocked.
Oh,
But no, you're on the right path. What will be low in an understocked stand? Mortality, right? Now, what will be high in understocked stands? Ingrowth, right? So you got to kind of balance those two. But it's usually, if we're interested in merchantable sized trees, we're going to be more concerned about mortality than stand-in growth. Maybe in the long run, we're interested in stand-in growth, right? But in the short term, we're going to be more concerned about mortality. And there's certainly going to be less mortality in an understocked stand. Less competition for resources, right? Now, of course, we're excluding things like lightning and so forth, right? We had no way to predict that. And then I say multi-aged. Well, here's why I say multi-aged. We used a local volume equation to get future tree volumes. Maybe that local equation was derived from data we collected today, right? We can go out and collect data on height DBH relationships and convert a standard equation to a local equation. But then we're assuming that that height-diameter relationship stays constant over time. Otherwise, our local volume equation isn't going to apply in the future. Well, as we talked about previously, in multi-age stands, that's a reasonable assumption to make. But that's what it looks like in even-age stands. That relationship changes over time. So we need to have some way of getting a future local volume equation, right? Not the current one. So those are the three, the combination of three things that this technique will work best in. Questions? Okay, have a good weekend.